Welcome, everybody. So good morning to some of you, good afternoon to some of you. So we've had this wonderful webinar for you all today. I want to introduce myself. My name is Laura Owens, and I'll be your host for our webinar. This is the Methane Guiding Principles Advanced Technology series, and today's webinar is entitled, Where Are the Emissions? Now, our goal today is to tell you a little bit about the learnings from recent remote sensing studies. These include both aerial and satellite technologies. And the focus is, what are the main sources of emissions in the oil and gas sector? What are the results of these recent studies? And we have a great panelist of experts when it comes to deploying and interpreting these remote sensing studies and their data. I want you all to use this opportunity to ask them any questions on this topic. They're a wealth of knowledge. It's a great opportunity to have them all here today in one place. But before I kick off, I want to bring to your attention some future webinars that will be hosted by the Methane Guiding Principles. First, a seminar coming up this midsummer on engineering solutions for methane abatement. The goal is how to target and prevent emissions from our highest risk sources, such as unlit flares, methane slip, and flare gas recovery. Please check your social media and your emails for a link to register for this event in the next couple of months. And then later in September, we will host a webinar on downwind and drone-based methods. Such monitoring solutions are offering accessibility in many hard-to-reach sectors of the globe, a lot of hard-to-reach geographies. They're workable within the equatorial climate gap for satellites, something we'll actually probably talk about today, as well as offering enhanced attribution and quantification. So we're really excited about these webinars coming together and hope that you'll keep an eye out and join us for those. So let me also introduce our panelists who will be sharing their insights from recent studies. And again, I encourage all of you to use the Q&A chat function. Your questions will be anonymized. We'll have plenty of time at the end of our short presentations in order to have a discussion and Q&A session with our panelists. And I also encourage you, go ahead and use the closed caption function on our Zoom platform. You can choose any language for closed caption as a part of this so that you can follow along with the discussion. So first up, I want to introduce Dr. Dan Cusworth. Dan is one of the key project scientists for Carbon Mapper. He works on algorithm development, validation, analysis, and applications of satellite greenhouse gas data sets across several industrial sectors. I can attest to this. Before working at Carbon Mapper, Dan was a part of NASA's Jet Propulsion Lab and conducted research at University of Arizona as well as Harvard. Second, I want to introduce Dr. Evan Sherwin. Evan is a research scientist at the Sustainable Energy and Environmental Systems Department at Lawrence Berkeley National Lab. Recently with Stanford University, where you may know him from his Meta series. Evan's research focuses on leveraging emerging technologies and data sets to find and fix methane emissions across the oil and gas value chain. And then last, I want to introduce Fanny Lagrange from Carbon Limits. Fanny's work spans working with satellite imagery and estimating methane and carbon dioxide emission factors along the oil and gas supply chain, as well as standing up CCS infrastructure projects from Africa to Norway. So we have this great group of panelists. Again, I encourage you to drop your questions in the Q&A function. And we're gonna get started by having our first panelist, Dan, start with his topic. Dan, up to you.
Great, thanks so much for having me. Let me share my screen here. Is it visible? Can you see my screen? We good? Okay. Well, thanks again so much for having me. It's really a pleasure to be here and talk about quantification and what the role of satellites are in quantification and identifying emission sources. And so I'm Dan Cusworth, the science director at Carbon Mapper. Just to level set a little bit, I always like to show this plot, which represents the general global methane budget. among the various sources and sinks of methane. So we're talking in particular about fossil fuel and oil and gas emissions. Of course, that's only one part of the larger picture of methane emissions and sinks globally, and one part of the anthropogenic human-caused component of methane emissions. But you might look at this, you might think of, well, where do I live? What do I need to monitor and measure? And what can I do from space? And so here's just a graphic that compartmentalizes current and near future missions that have some capability of measuring some methane emissions from space. Sometimes I call this orbital platforms, and that's more jargon, but space-based satellite sensors. And you can kind of put this into two main categories. There's a class of satellites that we commonly refer to as area flux mappers. That's what this top component is here, this top ring, and that would be the GOSATs, the TROPOMIs, the methane sats of the world. And what these do very well is look over a large area at fairly coarse resolution, but to constrain total emissions. And so this would be the total flux at the scale of a basin, at the scale of a country, at the scale of a region, to get an estimate of what the total flux is. And so this would be the total flux from all of those sources that I put in that previous slide. Now, if it's an oil and gas dominant basin that you're looking at, then the majority of that flux, that total emission, would come from that sector. But that's what these satellites are designed to do. There's another category of satellites that are, we call sometimes point source imagers. And this is the carbon mapper, the GHG sat, the Prisma, the Nmap, the EMIT, et cetera. And the difference here is that these are very fine spatially resolved instruments, so they can get down to the scale of tens of meters for their measurement of methane concentrations in the atmosphere. But the trade-off that they make with that is that usually they don't look over as large of a region, and their sensitivity is not quite as high as an area flux mapper. So you can think of these point source imagers as being able to do very well at capturing facility scale measurements, but only for a certain class of emissions. So for large point sources, or what are sometimes called super emitters. And maybe in a more graphical cartoon form here, you can imagine, here's a picture of an oil and gas basin, and you can see hundreds of oil rigs across that basin. What's likely going on in a place like this is that you have lots of small emissions that are just coming from oil and gas operations. So every one of these pump jacks in this oil and gas basin is emitting some small component of methane. And you put all of that together and it creates an area source, a total flux. The area source mapper will be very good at quantifying what that total emission is, that blue emission, but they won't be able to disentangle what the emissions are from each piece of infrastructure in particular. On the other hand, those point source imagers, let's say that there were a few of these pump jacks in this region that maybe were malfunctioning, maybe they were undergoing some maintenance, and they had a very disproportionately large emission source. So they were emitting at a super large emission rate relative to everything else. Those satellite instruments, because these are individualized locations of high emission, could be able to quantify and identify the emission sources. So you can think about, from the satellite platforms we have currently or that are going to be proposed in the near future, an ability to constrain a total emission across an area and be able to identify some individual point sources within that region. Now, there's no satellite capability, I'll just put as a caveat, that would be able to measure from space every single individual piece of infrastructure for what its emissions are. It's kind of that combination, and maybe put into this form, into an equation. And I apologize for putting an equation here, but this is an important point: is that the ability to measure within a basin individual pieces of infrastructure comes down to three central elements. And so again, if you're thinking about, I want to measure facility scale emissions in an area, and that's what my concern is, then what you want to think about are probably, and I want to do it using satellites, then there are three main considerations that you'll want to think about. And what I call this is observing system completeness. So how complete am I in terms of my observing capability? And this could be used for any platform. This doesn't have to be satellites, this framework, but let's talk about it in the case of satellites. So one driving factor of how complete you'll be able to observe emissions in your basin has to do with this term called CD, but really it's a detection limit sensitivity. So, it's an important factor. My instrument I have might be sensitive only to emissions at a certain level. I might have a limit of detection that's 100 kilograms an hour. So that means everything that's at 100 kilograms and above, I will likely be able to detect and quantify. Everything below that limit, though, I won't provide any information about the emissions. There may be an emission there. There may not be an emission there, but my instrument will not be able to make that determination. There's another axis here to think about, which is spatial coverage. So if I have a satellite, I'd want to say, well, how much of this area am I actually feasibly able to observe? And this is very important, is that not every satellite system that we have can observe every region completely over the course of, let's say, a month or a year, due to limits in terms of the instrument itself and how much it can observe. It may be more complete or less complete than another satellite in terms of the spatial area. So if I'm concerned about a basin, how much of that can I observe over a certain period of time? And the last factor is related to this. It is just the temporal completeness. So how often can I observe my basin in time? So this allows me to characterize the variability and the intermittency of potential emissions I see in the basin. So some of these things are set by the instrument sensitivity and the optics, that would be that detection limit. And the other components, which are equally as important, if not more important, have to do with how many observations can I make within my basin with satellite observations. So these are key things to consider when thinking about what satellites can do. And maybe just put as a little bit of a checklist, again, if you're thinking about, I want to leverage satellite information within my area of interest, then these are some questions you may want to ask yourself, which is, what is the spatial extent of my area of interest? What are the environmental factors of my area? So like, how much sunlight is typical in that region? How bright is the ground in that region? Most of the satellites that are on orbit, they rely on reflected sunlight in order to make their measurements. So if you're in a region that is, that is not very bright, how much sunlight does it get in the wintertime, or that has very dark surfaces, you're in a forested grassy area as opposed to a bright desert, that's going to have impacts on what the detection limit is of an instrument. Then, similar to that, how cloudy is my region? If it's very cloudy, most of these satellites, whether it's an area flux mapper or a point source imager, are going to struggle within that region. So these factors can all affect that detection limit, temporal revisit, and spatial completeness for satellites. And they're important things to keep in mind when considering using satellites in a region. Here's just an example from some studies we've done, though, where we were able to leverage both the area flux and the point source imager together in regions. Here's in the United States, 5 different basins that we surveyed with area flux mappers, which would be these blue bars. And then it wasn't satellites, but it was airborne remote sensing, where we quantified that point source component of the total emissions, and that's what these red bars are. And what we could then do is disentangle how much of the total flux that we quantify from all sources, from all emissions in that area, how much is coming from the point sources in particular, or you could say the super emitters in particular. And we could create a budget to try and understand what's the contribution of these disproportionately small in terms of infrastructure, but disproportionately large in terms of emissions. What's their contribution to the total flux? And we found it was significant. Here's another example. You could think of this as a LDAR approach, where we worked with a carbon mapper, worked with a state agency, the Colorado Department of Public Health, to provide data to them with very low latency. And so we flew airborne campaigns in Colorado, in the Denver-Julesburg Basin in Colorado. We processed the data and delivered emissions data and geolocated emissions data to the state agency within 72 hours. The agency then attributed each of these emissions to operators and made a determination of whether or not they would immediately go out and notify an operator of an emission to try and mitigate it. What we found was that with that low latency sharing and providing that data with someone who had the experience on the ground to go get information about it, we were able to mitigate many of these fugitive leaks that we found, and they were quite significant in terms of emissions when you added them all up. Here's just one example of that survey, and here it is in graphical form. Here's a aerial picture of an area inside the Denver-Julesburg Basin, and this arrow that I have is pointing to a wellhead that at the time we flew it with, this is again an airborne technology, but similar to what you might expect with satellites with some caveats. When we overflew it, we saw large methane plumes emanating from this wellhead, and actually the plumes themselves were blowing into a populated area. This was a mobile home park that the emissions were blowing into. We first observed it on the 9th of September. We observed it a second time on the 12th. We then, after that second observation, Colorado went to send an inspector out to verify the plume. They fixed it a week later, and then we did repeat overflights, and we no longer found a detection. So again, here's a timeline of kind of what it takes in that LDAR case with satellites being able to transfer that data to an operator for them to be able to use it. So I'll just leave it there, and I'm happy to take any questions in the discussion portion. Thank you.
Thank you so much, Dan. I think that was an amazing level set for this discussion. So next we have Evan, who will kick us off with his his conversation, and we'll be back in a minute.
Hey everybody, just decided to share the whole screen to make sure presentation went through. I'll be talking today about point source methane satellites and to some extent aircraft. And there we go. So where were we in the last decade? We setting the stage for the implications of satellites. In the 2010s, there was roughly a decade of vehicle-based studies taking systems like this, going downwind of oil and gas facilities and non-oil and gas facilities, taking measurements using concentration meters on poles, things along those lines. And after millions of dollars, huge amounts of time spent in the field, teams of researchers were able to assemble about 1,000 well site measurements across the United States, and then some more than that all across the world. And this was a huge advance for our understanding of methane emissions, for our science. This was summarized and sort of synthesized and worked by the Environmental Defense Fund in Mark O'Mara's 2018 paper, and Ramon Alvarez and others also 2018, finding that methane emissions overall from oil and gas systems were larger than we might have thought in many cases. I'll note here that in the vehicle-based site level measurement literature, there's not much above 100 kilograms per hour. And based on Dan's talk, that you can guess why that's an important number. Then remote sensing came into the fore in a big way that it just had we just hadn't been able to do beforehand. This is a picture from one of Dan Cusworth's papers, flying over the Permian. This is just one scene over a much larger survey, and each one of these emissions is pretty large. Most of them are above 100 kilograms per hour. So that raises some questions. First, does remote sensing work when an aerial or satellite-based instrument sees a large emission? Does it really see a large emission? And secondly, what do these findings of these very large emissions, assuming that we believe what we see, what does that mean for our understanding of methane emissions more broadly in our efforts to find and fix methane emissions? Well, thankfully, my collaborators and I at Stanford University were able to just go out into the field and test many of these different systems. So we did controlled methane release testing. This is the release apparatus we used in our 2022 campaign. We had multiple deployments to test out pretty much every aerial methane sensing platform that's available, at least in the United States, as well as all the satellite-based platforms that were available at times we conducted the surveys. Big shout out to the team, particularly to Dr. Sahar Al-Abadi, who led the 2022 on the ground deployment. And what we find is that this, I'll focus on satellites mostly today. The satellites, pretty much work. Here we have here 3 different satellites out of 9 that we tested in 2022. We tested 5 in 2021. And the rows here are the different satellites. These are NMAP is a European satellite, ZUN1 and GovN5 are both Chinese satellites. All of them are targeted methane sensing instruments in the sort of the middle range of sensitivity, I would say. And the columns here are the different teams that were analyzing exactly the same data. So what we see here in this column, for example, is multiple different teams looking at a 1 ton per hour methane emission. And they're estimating, it's all sort of order of magnitude, pretty close. They're not all getting the same number, and they're not all estimating the same shape exactly of a methane emission. There's some variability in how one processes the data, and the question of what is the shape of a methane plume is actually kind of a philosophical question. But one thing that's pretty clear to me is that they're all looking at the same thing. They might be looking with different sort of types of sensitivity, one could say, although even that, maybe that's not the right way to describe it, but all these shapes look like they're, different pictures of the same thing. And I would say the same is true for the other 2. And then we've got pictures of all the rest in the paper. Here's another shot of our setup. I won't go into too much detail here, but it's a pretty good story on the quantification side too. We have here, this is the metered emissions we were emitting from the ground. Here are the estimates that came from each of the teams analyzing satellite data for each of the 9 satellites that we were working with. And this was single blind. We did not, other than the fact that there was going to be a test from this date to this date, we didn't convey any information about what we were doing. And what we can see here is that, yes, there's scatter in the estimate of any individual data point, but taken on aggregate, and this is sort of on aggregate across different satellites, because we just don't have enough data points to say that much about individual satellites. But taken on aggregate, there doesn't really appear to be a lot of bias. The perfect 1-to-1 agreement would be this black line, and if we fit to everything, we get, instead of a slope of y equals 1, it's 1.1. So looking pretty good. Of course, we need to do more studies to really flesh out some of these numbers for individual satellites. And also on the detection side, I didn't include a plot here, but we did not get any false positives. That's not to say that it's impossible to have a false positive, but I would say at this point, if a satellite-based system or an aerial system says it finds an emission, then probably found an emission, and the quantification is probably pretty good to within statistical uncertainty. So more broadly, what does this mean, suppose? So if we take for granted that satellites work, and I think the evidence suggests that they basically do, what are they going to see? This is work from a recent paper of mine published in the journal Nature earlier this year that takes aerial measurement campaigns from 6 different regions conducted by Carbon Mapper, Dan Cusworth and his team, as well as by Insight M, formerly Kairos Aerospace, in across 15 different campaigns in these 6 different regions. And every dot here, more or less every dot here, is a well site that was measured by one of these 2 aerial methane sensing platforms. And the black dots are the remaining wells in the US that did not get measured. So that's a pretty good fraction. We're talking about 52% of onshore US oil production and 29% of gas was covered. And in many of these, in all but one of these regions, we were able to get very comprehensive data. More than 80% of production, more than half of the assets. I should say all the data are anonymized in the study. And what we find is that there is there are large emissions everywhere we looked. These are 5 of the regions. I can't show the 6th. And the blue dots are emissions at well sites where production's taking place. The red dots are emissions at midstream facilities, such as compressor stations, gas processing plants, pipelines. And in all the regions, we see some dots, but how do we translate this into a more sort of the numbers we want to know, the total emissions from a region or the distribution of emissions from this, how many small ones, how many medium-sized, how many big ones. I should say most of these are above 100 kilograms per hour. And I should have animated that a little better, but that's okay. What we see here is the distribution of emissions across different sizes. So this is the Permian Basin, and this is emission magnitude per site for well sites where production is taking place. And then this is cumulative emissions from sites emitting at least that much. So for example, well sites emitting at least 10 kilograms per hour in the Permian account for somewhere between 80 and 90% of total emissions by our estimate. The red here is what the airplanes directly saw, our estimate of emissions from those detections. And the black is filling in the smaller emissions using a state-of-the-art emission simulation tool. And what we see here is first off, the red, what the airplane saw is coming from a pretty small fraction of sites, roughly 1% of sites in the Permian, accounting for 50 to almost 80% of total emissions. And if we think about satellites with who are able to see everything above, say, 100 kilograms per hour, or even a few hundred kilograms per hour, if those are deployed with as Dan pointed out, enough completeness that through a large constellation of satellites or with high revisit time, if we're able to look at a lot of the area, then we could see potentially half or more of total emissions. And even a system that's less sensitive, like the Sentinel-2 or Landsat-8 satellite that's able to see above somewhere like maybe a ton per hour, maybe a little more, that would see a pretty significant fraction of total emissions. And that said, that's not universally true. If we go to a basin like the Denver-Julesburg in Colorado, there were definitely emissions detected in the aerial campaign, but a lot of the emissions were on the smaller end. And we need more sensitive instruments if we want to focus on the bulk of emissions, somewhere like the Denver-Julesburg. With that, just a quick pitch for the Methane Emissions Technology Alliance, which is a webinar series that I help run on methane emissions technology. You can find more at these links, or if you just Google Methane Emissions Technology Alliance. And with that, thank you very much.
Thank you, Evan. It's really shaping up that these aerial remote sensing technologies have incredible capabilities, and I think we're going to see a little bit more of that demonstrated from Fanny.
Yes. Can you see my screen?
You're good.
Yes. Okay. So hi, I'm Fanny, a consultant with Carbon Limits, a consultancy company working among other topics on the decarbonization of the oil and gas sector. And I'm very happy to share with you some insight of an ongoing project in which we are identifying and estimating the cost of mitigating methane super emitters. So I will present the motivation of this work, the methodology, and some preliminary results. So first, why do super emitters matter? So as you can see on this graph, super emitters represent a small percentage of events, but when they do emit, they represent a significant percent of total emissions. So for instance, if you want to mitigate one super emitter, you would need to reach out to one operator and you could have a significant impact. So for these reasons, they represent a low-hanging fruit for mitigation. But the question is, what are the global sources of methane super emitters? And in the case that we can identify them, how much, what would it cost to mitigate them? So to answer these questions, we got some GHGSat imagery with plumes, emission rates, coordinates, providing 2 years of observations for hundreds of oil and gas unique sites, and for almost a global coverage. And in addition, we used Google Earth aerial imagery, for instance, to identify if it was from floating roof tanks, compressor stations, or ground flares, or any other type of emission sources. And everything was based on carbon limits knowledge of oil and gas infrastructure and previous field experience. So it's not an exact science, but we have been able to identify most of the emission source. Then, for each emission source, we estimated an annual emission rate based on observations with and without detections and emission rates, and a Monte Carlo simulation was performed. So now let me show you one of the most interesting results of this project. So we have been able to identify super emitters in 37 oil and gas producing countries, spanning 5 regions, and accounting for a total of approximately 1.5 million tons of methane per year. So as you can see in orange, flares represent most of the annual emissions, but emission profiles vary from region to region. For instance, in Africa, we have what we can see is very different from what we can see in the Caspian region. And so what is important to note here is that we cannot apply a blanket action plans everywhere and expect the same results everywhere. We really need to design and to implement mitigation plans individually to each regions. So then if we aggregate data for the 37 countries, we can get the relative annual emission rates per emission source. So here we can see that, so on this pie chart, that flares represent almost 60% of annual emissions, and most of them are elevated flares. And then we have gathering and transportation pipelines representing in total 16%, and it was mainly observed in remote areas where we have limited people working there and available to monitor emissions. And finally, it's important also to note that a non-negligible number of sources, so 10% here, cannot be identified only with a desktop analysis. But we will come back to this later in the limitation part. So now let's focusing on flares that represent almost 60% of the total annual emissions. So to better understand the root causes and the behaviors of these flares, we used the VIRS flaring data. And so just for information, we have been able to identify 283 flares, that were emitted, which is a lot. And among them, 28% here were burn or dump pits with no observed flaring, meaning that it was not lit. And so these burn or dump pits may include oil and associated gas. So for these reasons, mitigation option could be a further separation, oil collection, or even further gas use or flaring. And then we have 34% of the flares that are elevated flare with no observed flaring. So again, it means that the flare was not lit. And so it can be for different reasons. It can be intentional, but maybe also it's because the equipment is not working as designed. So yes, it needs to be improved. And finally, we can see that 38% of our flares are elevated flares or burn pits with observed flaring. So it means that it leaks, but that it's malfunctioning. And what is important to see is that this 38% of flares represent a total of 62%, represent 62% of the total emissions coming from flares. So it's a lot. So it means that the system is working, but is malfunctioning, and we have periods with high inefficiency or even unlit periods. So in that case, investment in improved equipment, monitoring, and even awareness of the site personnel is very important to consider. And all in all, for all the methane emissions coming from flares, investment can be large, but it offers opportunity to significant reductions, because as you can see before, flares represent almost 60% of the total emissions that we have estimated. So of course, in any study we have limitations, and even with advanced technologies such as satellite, as it was mentioned in the first presentation. So for instance, here we only see what is targeted by GHGSat and what satellite can see, so which is limited by clouds, reflectiveness of water, of snow, and also we can only see what is above a specific threshold. And in our case, it was 100 kilograms per hour, which allow us to only identify super emitters, but as mentioned before, super emitters already represent a significant percent of the total emissions, so it's not negligible. But we have an increasing coverage and satellite capability that will allow us to even better understand methane emissions in the future. And finally, of course, when we have a high density of equipment, it's more challenging to identify the real source of methane emission. And it's also challenging when we cannot even see any equipment in the area of emissions. And to finish, as part of this analysis, we did not include operator inputs, so we were not able to confirm emission sources that we have identified, and some emission sources are not identified at all. But it's important to keep in mind that effective mitigation requires on-the-ground knowledge and people on site. And just to give you an insight from another project, so as part of another project with OGCI, we had the opportunity to reach out to operators, and they were very interested in mitigating their emissions, and many of them were very motivated. So, but the only thing is that at the end of the day, they are still oil or gas producers, so they may not have the capacity and the availability to work on this daily. And if you have more questions on this project with OGCI, my colleague Mazen and I would be very happy to answer a question in the question time. And then the next steps. So now that we have estimated the total annual emissions from super emitter, what are the costs of mitigating these emissions? In parallel, we are also analyzing methane emissions from super emitters from other sectors, such as the waste sector, and a white paper, not an academic paper, but a white paper is coming soon, so stay tuned. And that's all for me. Thank you very much for your attention. and looking forward to hearing your questions and feedback.
Thank you so much, Fanny. I think we have one quick follow-up question for you. What's the CE to DRE % threshold that you use to assess if a flare is burning or is not functioning as designed?
So you mean what? Yes, so it's just if in the dataset VIRS we have information on the flare or not. So it's it's not it was not a specific threshold. It was just if we could see the flare in the database or not.
No, thanks for addressing that. Well, I wanna thank all of our panelists for giving us this great foundation of information. We're going to just take a few questions, but I'm going to start off with something that I think Fanny, if you could address first, especially in your project, but everybody else, please jump in. How important is attribution of the emissions? It sounds like you guys use Google Earth, but in your ability to be able to do this type of analysis, how important was attribution, and how successful were you in that regard?
So it was a lot of hours spent on trying to identify the source of emissions, and we were several people working on this because we had to base this assessment on our different expertise. But I think yes, also we had different level of certainty because identifying a flare is quite relatively easy. But for instance, as mentioned, when we have a high density of equipment, it can be more challenging. So in that case, we can base the identification on the intermittency, also on the amount of methane that is emitted, because we know that some emission sources can emit more methane than others. And yes, I don't know if my colleague Mazen wants to add something.
So thanks a lot, Fanny. Exactly as you were mentioning, there's a list of criteria that we were using to identify the emission source. One of them is the intermittency of the plume, how many times it was detected during a certain period, how frequent it was, emission rate by itself, the volume, type of equipment, the context in the country, because we have experience in several regions worldwide, and this experience, we know through this experience that some of the common practice in some countries can lead to emission. So this experience was very valuable, and also through our engagement with previous operator and under previous project, we had accumulated some knowledge about what can be the most common or most probable emission source for this kind of emission, knowing the satellite imagery and all the parameters that we have mentioned at the beginning.
Thanks.
Can I just share a little bit on the attribution? I would say it really depends on the use case you're looking at, what the requirements are for that level of attribution. So if you're doing a leak detection and repair, you want to make sure that you get that operator really right. And the person who owns that asset, you want to make sure they're really correct. And so if you're using Google Earth imagery to do that, you're going to get part of the way, but you're not going to get all the way. You probably need some GIS, Global Information System database that is very current, because if you're not in a place where it's a nationally owned oil and gas company, if it's a place where there's maybe multiple operators within the region, it could be quite difficult to disentangle. This is the case in the United States. But if you're not doing leak detection and repair, and you might only be concerned about separating between, is it upstream versus midstream? Is this a pipeline? Is this a compressor station? So that if you're trying to come up with an estimate from all that infrastructure, or an intensity from all that infrastructure, you've at least attributed it to that segment of the supply chain. So I would say it's very complicated, but it's very dependent on the level of analysis. and use case that someone is looking at.
So maybe that leads into our next question, which is, if you were to be advising, maybe it's an operator, maybe it's a government on LDAR, using satellite and remote sensing technologies as part of your LDAR strategy, what recommendations or what learnings would you share with them in generating that strategy? And I was thinking, is it have to do with potentially the environmental conditions that you have to be aware of? Is it the follow-up procedures that they have to have in place? Any insights on that?
Yeah, I'll just go quickly. I mean, I will say I'm not an expert in implementing LDAR programs, but from the evidence we've had from seeing satellite observations, you should be prepared with being able to take aerial imagery and attribute it to operators. So databases of operator or asset level information. I think also understanding that satellite, the best spatial resolution that the satellite's going to give you is within 30 meters at very best. That's kind of the pixel resolution, but you imagine the atmosphere, it's a lot of turbulence. You see a plume, maybe exactly it's in this 30-meter place, but probably more likely it's about 100 meters. So again, being prepared to use it for LDAR within a 100-meter scope, would then follow up, would kind of want to look at all of the infrastructure within that 100 meter domain to ultimately see where exactly that leak is coming from. So I do think being prepared for a handoff from what the satellite is to kind of refine what ground-based leak detection protocols would then uncover. They really have to go hand in hand, but it can be extremely powerful, the satellite information, because you can go from what might be a daunting hundreds of thousands of pieces of infrastructure to some isolated hotspots, and just have to go and follow up. So I think there's a real good handoff that would work for efficiency there, assuming that those things like attribution are in place, and readiness to act on data.
Yeah, and I know that one real advantage operators have that researchers won't necessarily have is operational data. Once suppose satellite gets tasked somewhere, sees a large emission, for researchers like Dan and myself, we don't always know necessarily what was going on in the facility in terms of, was there a maintenance event, was there's some sort of anomaly with pressure at some point, but presumably the operators are in most cases going to have operational data that'll make it possible to find the signatures of, well, what went wrong in the first place that resulted in a large emission. And that's one area that I think that satellites can be really, really helpful. Is hopefully my hope is that the more we do these large scale surveys that find the really big emissions, we can figure out in advance what sorts of what's resulting in them in the first place, so that we can just take preventive action.
Excellent. So let me address a very specific question around its applicability for certain geographies. We have one question that asks about how effective are these technologies in the offshore environment. Any reflections on that?
Yeah, I would just quickly say I think that still needs to be tested in the offshore environment for satellites, the ones that I showed in my presentation. In order for them to work, they have to rely on something called sun glint. So that is pointing the satellite in such a way that the surface becomes very reflective. You can imagine if you've ever been to a swimming pool and you look at the pool at some weird angle, you get this blinding light in your eye. That's kind of what you need in order to make a measurement from a satellite platform in an offshore environment. So it's a little bit different than the standard imaging mode. So I think, we've shown with airborne campaigns, and I know GHGSat has done some and some other remote sensing technologies, that they can definitely detect plumes if the conditions are right for sun glint. There has not been the same level of testing of emission rate quantification in those environments, though. So I think we're there to suggest that, yeah, it can be done from satellite platforms. There's probably some more in terms of quantification that needs to be tested.
Evan, that sounds like a challenge for the controlled release team. Next steps. But is that something, if you're again an operator that's developing a strategy, and I say I know that I have denser than typical cloud cover, say I am in an offshore environment, is it still an option for me to request a data over my area, and what kind of special concerns would I need to take into consideration?
Yeah, I would say just, kind of two things related to that is that for many of the point source imagers like the Landsats and the Sentinels, they are not doing any special operations in terms of their primary mission. These are, government agency funded satellites that have a primary mission, and they just collect data. So if you opportunistically get a sun glint condition in an offshore environment, then yeah, maybe that could be used, leveraged by someone to do a detection, but it's probably not very reliable. Other satellite companies that are task satellites that are private, if they have a sun glint capability, that's something that a person could ask for. But just to level set and to be realistic, because you need those sun glint conditions, there are just not as many observing opportunities in the offshore environment with the current suite of satellites as there would be for onshore. So going back to the completeness metrics of your spatial coverage and your temporal revisit, those are going to be severely limited compared to onshore for the current suite of satellite remote sensing capabilities. And it's just be good to be aware of that. And maybe in the future, someday we'll build more, but it will change.
Now, this question of clouds, it's an interesting one, and I pulled up a figure from our latest controlled release test. These are retrievals from WorldView 3, analyzed by Maxar, and from Prisma, analyzed by Nanjing University. And in both of these cases, an emission was correctly detected. But if you look here, these are the actual optical images collected by both of these satellites. You can see some clouds, and in this, can't really tell whether there are clouds or not, but we took some pictures of the sky from the ground, and there were clouds on each day. If we zoom out, then we see, oh, it was pretty cloudy, but we got kind of lucky here, and we got lucky here too. This is the area that we were. And to me, what this tells us is if an area is fully overcast, then that's not an observing opportunity. But under conditions where there are sort of patchy clouds, it is possible to detect emissions correctly in the places where the clouds are not present. That said, it would kind of be a gamble to if one had a decision to task a satellite on this day, it'd be kind of a gamble to decide to spend an acquisition in this type of circumstance.
And just real quick, there's a follow-up question about snow. So, Dan, you mentioned reflectivity is good, but it sounds like snow is a problem.
Yeah, so snow is very reflective in the visible wavelengths. What we see with our eyes, it's not very reflective in the shortwave infrared, which is where these sensors are observing methane. But that said, it's not a deal breaker as well. So I would just think of in snow-covered environments, you're probably going to have an impact on your detection limit. I think it's not impossible, but that would be a thing to keep in mind. And these are ongoing tests that a collection of groups are attempting to do to have more controlled releases in a diversity of environments to really see, what ultimately is that detection limit scaling in a snowy environment versus a bright desert environment. But I would say just generally your detection limit will be impacted in snow.
So we're coming up to the end of our hour, and I want to just close out on a question really about what you all see as the future of satellites and remote sensing technologies. For example, there's a question that around the Colorado use case, which is, can this now be implemented as part of regulatory oversight in order to or determine compliance towards regulation? I think that's an interesting future use case if anybody feels like commenting on. So maybe we go to Fanny and Mason, and then to Evan, and then to Dan to close us out.
Fanny,
Sorry.
would you like?
Either one.
I can start, and then Fanny, you can complement Fanny. So satellite will play an essential role, especially in optimizing the cost and the full overview of the monitoring and detection of methane emission, because we see that LDAR has, or leak detection and repair campaign has some limitation. Satellite has some limitation, and that's why the combination between all the tools are necessary, especially from the regulation part, where regulators can use satellite to monitor asset and fields on their jurisdiction to make sure that all the operators are compliant. So from all these lesson learned from previous engagement, from the different point and product we have worked on, I think satellite is more and more proving their effectiveness as an essential role for detection, and more also for quantification of methane emission. And certainly it will push forward as with its role in both operation-wise and regulation point of view. I don't know, Fanny, if you'd like to add any point.
No, I don't have anything to add.
Yeah. I would say for the point source satellites, they can certainly be used to determine non-compliance. I think it would be challenging to use them to determine compliance. For the area source estimation methods, those could, I think, be used pretty effectively on a regional scale to determine sort of carbon intensity. I don't know if that's compliance necessarily.
Yeah, I'll just quickly say, I think with satellites, we're in this very interesting place where we have seen so much data that there's we should act on this data, but it's also a relatively new field. And so it's very new, but it's very compelling. In the United States, for example, just following up on that question real quick, there are new regulations, new oil and gas regulations that include carve-outs for remote technologies. Really, it's probably airborne technologies, not really satellites, but to provide more remote technologies into LDAR systems. They've also instituted a super emitter program. So anything above 100 kilograms an hour, if it gets shared with EPA, it requires an operator response. So I think avenues to just, if nothing else, provide more information for these detections to help us better understand their contribution to really, across all basins, across all regions, what is the impact of super emitters, which is what the point source imagers are really designed to do super well. It's going to be a critical piece. So.
Well, thank you all for that fantastic insight. So one last applause at home for our panelists. I want to thank you guys all for the fantastic questions. This is a recorded webinar, and you'll be shared a link to this to be able to give to your friends in the methane community. I hope you all will join our future webinars, and thank you so much for joining us this beautiful morning, afternoon, evening, wherever you might be. So have a great one. Thanks, everybody.